already studied the Rutherford's alpha particle scattering experiment. The experiment demonstrated that the radius of a nucleus was much smaller than the radius of an atom, and therefore the volume of a nucleus is about 10 to the power minus 12 times the volume of the atom. This shows that an atom is almost empty, and if you consider the atom to be the size of a classroom, the nucleus would be as small as the size of a pencil tip. What exactly is atomic mass? We can say that the mass of an atom is the total mass of subatomic particles in it. To be more precise, it is the mass of the total number of protons and neutrons present in an atom. Here we consider the electron to have negligible mass. The atomic mass is very small compared to the mass unit kilogram, and we have a different unit to express atomic mass. This is denoted as atomic mass unit, and it is denoted by small letter u. Since we directly cannot calculate the mass of an atom, we calculate it in comparison to the mass of a carbon atom. We consider the carbon-12, one of the isotope of carbon, as the standard. Therefore, one atomic mass unit is defined as 1/12 of the mass of carbon-12 atom. Expressing it in kilogram, 1 U is equal to 1.660539 times 10 to the power minus 27 kilogram. Moving on to neutrons, in 1932, James Chadwick conducted an experiment where beryllium was bombarded with alpha particle, and he observed the emission of neutral radiation. Even though the only neutral radiation known at the time was photons, Chadwick could successfully make the conclusion that the neutral radiation consists of a new type of neutral particles that are called neutrons. He was able to state the mass of this neutral particle to be almost equal to that of protons. James Chadwick was then awarded the Nobel Prize in Physics for this discovery of neutron. Therefore, we can state that the nucleus of an atom contains neutral matter in addition to protons called neutrons, and the mass of the neutron is 1.00866 U, that is equal to 1.6749 times 10 to the power minus 27 kilogram. A free neutron is unstable and it can decay into a proton, electron and an antineutrino. However, it is stable inside the nucleus. The nucleus of an atom therefore consists of tightly packed arrangement of neutrons and protons. As these two are heavy particles in an atom, 99.9% of the mass of an atom is concentrated in the nucleus. The positive charge in the nucleus is because of the protons, and a proton carry 1 unit of fundamental charge and it is stable. Considering the atom as a whole, all the electrons in an atom are outside the nucleus. If the number of these electrons outside the nucleus of an atom is denoted by capital Z, then for a neutral atom, the number of protons will also be capital Z. The total charge due to the atomic electrons can be expressed as minus Z times E, with E being the charge of an electron. Since the atom is neutral here, the charge of the nucleus thus will be plus Z times E. The composition of a nucleus can also be described by the number of protons and neutrons in it. If an element is represented by ZXA, then the atomic number denoted by Z is simply the number of protons in it. The mass number represented by capital A is the total number of protons and neutrons within the nucleus, or we can say that it is the total number of nucleons in an atom. If N represents the number of neutrons in an atom, then A is equal to Z plus N, that is the total number of protons and neutrons. The accurate measurement of atomic masses of elements can be carried out with a mass spectrometer. This measurement of atomic masses reveals the existence of different types of atoms of the same element that provides the same chemical property, and the only difference is there in the mass of these atoms. Such species are called isotopes. Isotopes are those elements that have the same number of protons and different number of neutrons. In other words, we can say that they have the same atomic number but different mass number. Practically, most of the elements consist of a mixture of several isotopes and their relative abundance differs from element to element. Example can be shown as the isotope of carbon and isotope of hydrogen. The isotopes of carbon is shown here. The carbon-12, carbon-13 and carbon-14 are its three isotopes with mass numbers 12, 13 and 14 respectively. We can see that in all the three cases, the atomic number of carbon is 6 and therefore every carbon has 6 protons. The neutron number of these isotopes are different and it varies like 6, 7 and 8 respectively. Another example is that of hydrogen atom. The three most stable isotopes of hydrogen are protium, deuterium and tritium. These isotopes form naturally in nature. Protium and deuterium are stable and tritium nuclei, as it is unstable, do not occur naturally and are produced artificially in laboratories. Isotopes of the elements do not all exist in equal ratio, or the relative abundance of different isotopes will differ from element to element. The number of isotopes also vary for each element. Also, the average mass of an atom is obtained by the weighted average of the masses of its isotope. We already know that as the atoms of isotopes have identical electronic structure, they will have identical chemical behavior also, and therefore these are placed in the same location in the periodic table. Similarly, isobars are the elements or nuclei with same mass number but different atomic number, and isotons are the elements with the same number of neutrons but different atomic number. Some of the examples of isobars and isotons are shown here. 16C6, 16N7, 16O8 and 16F9 are all examples of isobars, and 14C6, 15N7, 16O8 and 17F9 are the examples of isotons. More on nuclear characteristics, the various properties such as the size, relationship between its mass and stability are all discussed in the coming sessions. Let us summarize what we have learned so far.
Manorama Horizon. Learning made simple.